Natural selection does not optimize for structural elegance. It executes a minimal viable survival check, pushing to production any biological architecture that does not immediately trigger a fatal runtime exception. How do organisms operating with severely degraded throughput and unhandled exceptions avoid extinction? Consider the giant panda. It is a biological deployment suffering from a critical hardware and software mismatch. It runs a carnivore gastrointestinal firmware, an architecture strictly compiled to process high-density protein. Yet its primary input stream consists entirely of low-yield bamboo. To prevent a system-wide crash from this data type error, the organism must force 38 kilograms of physical intake through its pipeline every single day. The system did not fail. It is executing its code exactly as written. The architecture barely functions, allocating almost all available energy just to keep the background processes in idle. But a processing bottleneck is nothing compared to a fatal logic flaw in a maintenance script. The three-toed sloth operates at a constant 40 to 45% metabolic deficit. A single leaf requires 30 days of processing time to clear the internal buffer. This extreme latency introduces a severe security vulnerability. At precisely 1600 local time on any given week, the organism initiates a mandatory system evacuation. It must descend from the canopy to the forest floor to purge its waste. During this single, agonizingly slow maintenance cycle, 50% of all recorded system terminations occur. The organism is offline, exposed to hostile agents, and permanently deleted. Access your local logs, observer. What legacy public infrastructure in your specific city or country operates with the same catastrophic inefficiency as the Panda digestive pipeline, yet somehow hasn't crashed? Submit your report in the comments below. We tolerate these design flaws because metabolic inefficiency is merely a slow, silent vector. The true disaster materializes when an organism's active defense modules fail completely in real time. Take the Mola, the ocean sunfish. It navigates the water column without a functional mobile rear bus. Its propulsion mechanics are critically degraded, rendering rapid evasion impossible. As a result, it suffers a staggering 99.999% larval packet loss. By any standard metric, this architecture should have crashed millions of years ago. Instead, it compensates through pure brute force fault tolerance. It masks its catastrophic mortality rate by flooding the pelagic environment with 300 million simultaneous instances of itself in a single execution. The ocean simply cannot process the deletion of every single node before at least one reaches maturity. It survives via a massive buffer overflow of its own making. But brute force requires massive resource allocation. What happens when an organism optimizes for an isolated sandbox environment? The Strigops habratilis, the kakapo, evolved in a closed network, entirely free of predatory mammalian nodes. Without external threats, the evolutionary compiler deprecated its flight modules to conserve energy. It became a heavy terrestrial anomaly. When invasive mammals were finally introduced into its network, the system did not fail. It executed its code exactly as written. The kakapo possessed absolutely zero fail-safes. A ground-dwelling architecture with an obsolete defense protocol met agile, highly optimized predators. The resulting cascading failure nearly wiped the entire species from the registry. Sometimes, rather than facing total systemic collapse, the biological code executes a desperate workaround. Consider the Ambystoma mexicanum, the axolotl. Facing environmental stress that threatened its adult parameters, the organism did not deploy a forward-facing patch. It triggered a state of neoteny, forcing a permanent rollback to its aquatic beta version. It permanently disabled all terrestrial migration protocols just to preserve its localized tissue regeneration scripts. It lives its entire life cycle in a state of arrested development. Observer, if you monitor failing architectures from your corner of the globe, initialize your subscription sequence. We document these critical systemic vulnerabilities every week. We have examined architecture surviving through sheer volume, obsolete hardware, and unstable rollbacks. But there is a fundamental difference between limping along on unstable patches and finding a critical exploit in the actual system shutdown routine itself. The Turritopsis dornea operates on a completely different logic model. It is a hydrozoan measuring a mere 4.5 millimeters, navigating the Mediterranean and the waters of Japan. When environmental stress parameters such as starvation or physical damage breach the critical threshold, this organism does not trigger the standard cellular termination sequence. It does not die. Instead, it intercepts its own shutdown command and actively rewrites its current state directly in memory. It executes a systemic workaround known as transdifferentiation. The adult organism effectively wipes its specialized somatic cells and reverts them entirely to a pluripotent state. It restores the original factory backup, converting a failing adult architecture back into a base-level polyp colony. Biology bypasses planned obsolescence by reinitializing its own boot sequence over and over again, achieving theoretical infinite uptime. They survive not through perfection, but through brute force redundancy and environmental luck, proving that evolution tolerates any legacy code that barely compiles. The ecosystem is not a masterpiece of engineering. It is a precarious network held together by spaghetti code, surviving daily through sheer statistical anomaly. Log off this session and proceed to our analysis of the catastrophic memory leak that brought down the Theric 25 infrastructure. End of file.